Chapter 2.5, Architecture. Our introduction to architecture tells us that architecture is three-dimensional design that surrounds and influences us. It connects us to our history. It suggests feelings of permanence. It is produced by architect, interior designer, and landscape architect. Of all the art pursuits that we will talk in this class, other than earthworks, architecture is definitely a form of art that must be produced by a group of people, not just one person. I mean, obviously, one person can build a house, but typically you need a large community to come together to produce a piece of architecture. Architectural engineers work to create a balance between tension and compression, which is basically push equals pull. Each building material must resist compression or tension differently. And if balanced correctly, a building can then stand for thousands of years. This is an exquisite mosque that is designed by Stenan, which exists today in Istanbul, Turkey. It was created around 1557. And as you can see, it was designed by Turkish architect Sinan. It is an elaborate architectural space which includes a dome and half domes. It is perfectly balanced. That has an enduring design that has lasted now for more than 500 years. This is a Taos Pueblo that was created roughly sometime before 1500. It's located in New Mexico. And take note of this cubic design, which is a very strong way of building. Everything sort of is attached to one another, so all the buildings help the other buildings kind of stand up. It's incredibly solid. And, we can definitely say it's a successful piece of architecture. It reflects its community. The adobe brick can last, particularly in this environment, forever. And its character derives from the available materials of the area, sand and clay. So everything to make this structure can be found in the region, which also helps for repair, or if you want to make additions to the piece of architecture, it always helps to have everything at hand. The Soho lofts that are located in New York City are another example of, very successful pieces of architecture. People even today clamor to get their hands on a lease for one of these beautiful lofts in Soho, southern part of New York City. Again, modular design, very space efficient, really a perfect piece of architecture for the lofty spires of Metropolis. If we look back to the ancient constructions of architecture from our past, there are a few things we need to think about. The fact that ancient cultures derived their building materials from the earth, that stone, wood, and clay would have to be modified for use in construction, and that these raw materials could result in architecture that would transcend time itself. We're going to first look at the most basic load-bearing construction. This form of construction follows the direct process of piling just one stone or brick on top of another. Massive load-bearing works have been built throughout the course of history. This is Temple 1 in the Great Plaza in Guatemala. It was created somewhere around the year between 300 and 900 CE. And it is just a simple kind of load-bearing structure, almost a mastaba pyramid like from ancient Egypt, and created simply by stacking blocks one on top of the other. Because it is in this sort of pyramid shape, the load is transferred very precisely from the top to the bottom. Everything has something beneath it to help hold that load. So that push-pull is satisfied in this structure, and therefore, this temple would last pretty much for eternity. I mean, there'll be some weather wear just from the rain. Its location will, of course, force it to sort of, as opposed to the pyramids in Egypt, that get a lot less humidity or rain than precipitation than they do here in Guatemala. So it's going to wear faster than the pyramids would, but it will still stand up to the test of time. As we move away from a load bearing construction, we move along to post and lintel. To create an interior space, an architect must create a span or distance between two supports. In basic post and lintel construction, the lintel rests on top of two posts. Here we have a diagram that shows basically how a post and lintel system works. The only sort of drawback to post and lintel is you definitely have a limit as far as how wide this span can be. If you go too far, like if the lintel is too big, right? Like if this is our post and lintel structure, right? And we put too much space between these two posts, gravity is going to put so much pressure on the center of this lintel that it's going to crack and fall apart. That's the only problem with post and lintel is you're very limited as to this span, the distance you can create between the two posts. So that is the drawback, and we're going to see how that looks in these next few slides. This is an image of the Great Court at Temple of Amun-Re in Egypt. And here you can see the post and lintel system being used. You have your lintel above, your posts below. But see how many posts you have to put in to hold the structure up. You notice that there, and in the middle, we can't see it from this photograph, but there would be even more posts to continue to hold this sort of roof section up. Most of the roof has fallen in. Guess why it fell in? Because they didn't put enough posts. You have to have so many posts to hold up that much weight that eventually it's going to crack and fall. So that's the problem, is you end up having so many posts, you don't have any room in the interior of in this case, the temple. This is a temple located on top of the Acropolis in Greece, next to the more commonly known Parthenon. This is a smaller temple, but it's on the same hill as the Parthenon. And it's by Kallikrates, called the Temple of Athena Nike. And again, you can kind of see the use of the post and lintel system to create this temple. Now see, if you look one level back, there's another post, right? Again, you have to put so many posts in to hold up that roof. So it seriously affects the amount of room that you can have in the inside of the structure itself. Now, if you're going to have so many posts, they have to start having some kind of a certain degree of meaning to the work itself, and we can definitely see that in the posts that were used, these columns that were used in the architecture of ancient Greece and ancient Rome. The Greek temples, the posts that are used in these columns are sort of separated into three capitals. The capital is the top of the column. And you have Doric, this is Doric, this is Ionic, and this is Corinthian. Now, for a long time, people thought that this was like an evolution from left to right, that first came Doric, then several hundred years later, Ionic columns were created, and then they ended with Corinthian. But we've changed our minds. We've now determined that all three of these types of columns were created at the same time, and that architects would just sort of choose what type of column capital they would use. And typically it was because of what the use of the building would be. So if the building was just going to be kind of a very standard building with multiple uses, uh, a Doric column would be used. It was very generic. It didn't really have any sort of ornate aspect. And so Doric would be what would be used for sort of a very common structure. Ionic capitals all have this kind of scroll. Now, a scroll is associated with reading. This is before the use of codexes. So anything that you read would be put into the form of a scroll. So therefore, any building that had this scroll-like top, which is called an Ionic capital, would have been used for education, storage of documents, anything that had to do with knowledge or reading, libraries would have an Ionic capital. And then lastly, these Corinthian capitals, which were the most ornate, which would sort of have these sort of decorative leaves, and scrolls. It would have basically a little bit of everything. These were reserved for government buildings. So anything that had to do with the leadership of the country, anything that had to do with, anything to do with the state would use these Corinthian capitals as a way to designate that that's what the function of this building was. Here we have a diagram that shows us how each order of column are sort of divided into these architectural parts. So the bottom of all of these temples, the very bottom is called the stereobate, and then the last step is called the stylobate. You have the shaft of the column. You have the capital, which is here. The entablature is a very important part of any Greek or Roman building. Typically, the entablature would contain what's called a frieze, which would be basically a series of relief sculpture that would tell the story, maybe of the city in which the building was located, or even of the building itself. If it was a temple that was dedicated to a god, it might tell a great mythological story about that particular god. The very top is a triangular structure. This is called the pediment. And in the pediment would also traditionally be sculpture that would have to do with, again, the building or the city in which the structure was located. And then the roof, or also called the acroterion, which is essentially just the roof of the building, a roof of the temple that would kind of hold everything together. The structure that would change architecture to probably to the greatest degree in the ancient world would be the use of the arch. In early architecture, lintels, like I just said, could not span large enough spaces that the stone would snap under very heavy pressure. So the arch was a way to sort of solve that problem. They would use either corbelled arches. The Babylonians and the Mycenaeans would use the corbelled, and then the rounded arch wouldn't be perfected until Roman times. Now, it's really easy to see to pick out a corbelled arch. It looks very much like something if you were forced to build an arch out of Lego, right? Because essentially it's just stone stacking to sort of create a basic, kind of arch shape. And the reason an arch is very efficient is that unlike the post and lintel structure, when gravity is affecting, the force of gravity being pulled down onto the structure is evenly distributed down these legs, as opposed to sort of hitting the center of a lintel full. It's pulled to the sides. And so all of the weight then is held by these really strong columns, right? The posts actually end up holding the weight of the structure above it. And this is how, these structures are really strong. But now the problem with the corbelled arch is, again, you could only go so far because if you went too far, again, the force of the weight would eventually crack at least one or two of these bricks. And once two or three of the bricks would crack, the cracks would begin to travel down, and eventually the structure would most definitely fall apart. Here is an example of a building that uses corbelled and a corbelled arch structure. And as we look at it, you can see that it is held up obviously very well, but there has been some damage. Like if you look here in the center, there are cracks that have formed because of the weight on top of this structure. And you can even see how they've had to do a lot of repairs, like in this section, to the structure itself because of the effect of gravity on the corbelled arch. Now, a true arch, as would be perfected by the Romans, you can see how you don't have as much of an issue of the load bearing down on the center of the arch. In fact, the top of a Roman arch has what's called a keystone, and it is shaped basically like the very top stone would be shaped almost like a trapezoid. And then each of the other parts would be shaped something like this, like a flat bottom and then a curved top. And so then if you put another one in here like that, see, you start to get sort of this natural curve. The keystone, is what sort of locks the arch together and allows the weight to be channeled to the post, therefore allowing for larger spans. With an arch, you can go as big as you want. You can go as big as you want, and it can go as tall as you possibly want it to be, and it will hold that weight. This is an aqueduct. The aqueducts are still standing just as strong as they did when they were built in ancient Rome. And they are structures that were used to transport water from the outside areas of Rome into the city. They would span for miles and miles and miles. They're all hand built. And within each of these structures is like a small tunnel. And that's where the water would travel through these sort of completely enclosed structures all the way into the city, where they could be used to actually give most homes in ancient Rome, which is what made it different than every other civilization before it, had running water. Now, vaults are an architectural structure that it was sort of a natural evolution from the use of an arch. Now, the way a vault is created, so like if we were to see an arch like this, and let's say you wanted to create a structure, a very strong structure. Well, what you could do is then say, okay, well, I can build this arch, and then let's say I build another arch, right behind it. And then let's say I build another arch right behind that one. And I keep going and going and going, right, until I have basically like this sort of tunnel of arches. Well, that is a vault. In particular, that's called a barrel vault. They can span very large areas of interior space, and they were very incredibly important during the European Middle Ages. Where can we commonly see barrel vaults? Here you go. This is the Church of St. Madeleine in France. And essentially, if we look at most of these cathedrals, they are essentially just a large barrel vault. Why? Why is this significant in the building of Christian churches? When Christianity was in its infancy, it was basically considered to be just sort of a cult in ancient Rome. It didn't have a lot of members, and in fact, most people would try to blame the Christians for anything bad that happened in ancient Rome. It was illegal, and so most Christians had to worship underground in the catacombs of ancient Rome. So, because if they were found, they would be crucified or fed to the lions, or any number of horrible things would happen to them. It wasn't until Constantine, the ruler of Rome, would sort of convert to Christianity, and Christianity then would become legal, and Christians began to start building their own churches. Well, they had, for hundreds of years, they had worshipped beneath Rome in these catacombs, and the barrel vaults that held up the streets of Rome, right, was where they worshipped. So they sort of took that as part of their heritage, these barrel vaults, and therefore started to build their churches very much to remind themselves of these tunnels beneath the streets of Rome. This is one of the world's great cathedrals, Chartres Cathedral, and you can see that the one thing, though, that arches do is if they get too tall, you start to have to hold up that weight. And so Gothic cathedrals such as Chartres uses what are called buttressing. These large towers that you see on the outside of the church are not just decorative. They help hold up the walls of the church, these walls of the barrel vault. So for example, if we were to look through one side of the church, it would be this sort of vault. And even though you have all of this sort of weight being brought down through the legs, right, of the barrel vault, if it gets too tall, it could still fall over by wind currents that are blowing from the other side. So you had to sort of hold that weight up. So they started adding these other towers to the sides of those barrel vaults and then attaching them with this, which is what's called the buttressing, which are these kind of arches, these half arches that would again take more of the weight over into another leg. So then half of the weight was carried by the leg in the middle and the next half there. If they got even taller, they would add another tower and another flying buttress. So they can get really tall, but they have to sort of, inside they can get really tall, but in order to do that, you have to add more and more towers and buttressing to the outside of the structure. The next evolution for the arch would be domes. Now, domes are very much like an arch that is basically rotated 360 degrees. So what you're essentially doing is you're taking your arch and then you're spinning it. So it's like one arch, repeated around and around and around and around to create that dome structure. Usually at the very top, a hole would be left to sort of allow light into the interior of the dome. That would be called the oculus. Domes are very strong structures, again, because they're holding, each arch has another arch next to it, kind of helping to hold up the weight. And all of the weight then is dispersed outward toward the walls. This is one of the most famous of the domed cathedrals. This is the Hagia Sophia. It is located in Istanbul, Turkey, which was originally Constantinople when it was part of the Roman Empire. It was named after Constantine, the first Christian Roman emperor. And you can see the sheer size, how much space is located, within the Hagia Sophia. And that's because of this use of the dome. You don't have to have any columns. You don't have to have any sort of columns to help hold it up because all of the weight is distributed out to the walls. Look at the size of it. When we look at these people, you can kind of see the sheer size, the sheer magnitude of this structure. From the interior. They're magnificent. I've never visited this cathedral. I've only seen Gothic cathedrals like in France and in Italy. I would love to see the Hagia Sophia because it is supposedly amazing to stand in the center of this structure. Now, this domed structure is called the Pantheon, which is located in Rome. It was built in ancient Rome, somewhere around 100 of the Common Era. It was a public area for the senators to meet in public. So if you were just a regular citizen, you could come to the Pantheon and listen to the politicians argue with each other. And again, here is an example. This is a dome structure. Here is an example of the oculus from above. This is completely open. It never has any sort of covering. And what's interesting is because of the air pressure that develops within this structure, even if it rains, the rain doesn't enter that hole. It's pushed out because of the air pressure being blown up through the oculus. So even on the most rainy, stormy day, no water accumulates on the floor of the Pantheon. One very important part of the architecture of dome making is the pendentive. And your pendentive, so here you have four arches. You would have another one in the back here and then another one. So you'd have four arches to hold up the dome, right? Like, for example, in the Hagia Sophia. Well, that's all good and everything, but you would have this sort of triangular section that would need a little bit of help to sort of see, because you didn't want this section of the dome to crack and fall. So they would fill this area with sort of concrete to, again, continue that strength of bringing all of the weight all the way down into the legs, these sort of posts. And that triangular area is called the pendentive. The next type of architecture we're going to talk about is post and beam, or wooden architecture. The post and beam construction technique has been used to build some of the world's finest wooden architecture. One example of wooden beam architecture is the Horiji Temple in Nara, Japan. And it is one of the first temples in this sort of complex that was built in 607. It is an example of the durability of well-constructed wooden buildings. The use of cross beams and counter beams create this series of layers which help to support the roof. And one thing that is very typical in wooden structures like this, because it's lightweight but strong, that it has an impressive height. After the sort of perfection of building through wood, once iron became easier to sort of smelt, cast iron would become much more common within the building of architectural forms. Cast iron has been available since ancient times. Molten iron could be cast into the mold, in a mold to almost any shape. But it wasn't until the 18th century that it could be smelted into large enough quantities to build with it. This is a 19th century engraving that shows us a building that was made completely out of cast iron. It was called the Crystal Palace. It was destroyed during a fire, and then most of the other iron then was taken apart and used during World War II to build tanks and bombs to take on that funny looking little fellow with the weird mustache during the 40s. But we can see here in this engraving how magnificent the Crystal Palace was. And even today, if we look at a lot of modern malls, you can see how that same kind of architectural structure has continued into modern times. A majority of buildings that have been constructed over the last 50 years have used steel frame construction. Steel is a material made from iron and a small quantity of carbon. It is stronger than pure iron. It is less likely to break than iron and has even greater potential. Any building that you see in a large city like Houston, New York, Chicago, all of these skyscrapers are all built with steel. It was one of the only metals at that time that could withstand the sheer weight and tensile stress put on these buildings with their height, because you're not only having to deal with gravity, you're having to deal with wind itself pushing the edges of the building. So steel was a material that very much made buildings such as this, the Wainwright Building in St. Louis, possible. Louis Sullivan, who many consider to be the father of modernism, is the person who pioneered the use of steel and created the first skyscrapers. He believed in this idea, which would be triumphed by architects such as Frank Lloyd Wright, that form follows function, that you should always have a versatile interior space that serves the people who live in it or work in it to the highest degree. The exterior of the building reflects the elements of an actual column, as we've seen for hundreds and hundreds and hundreds of years. One of the most important materials that has been used in the building of architectural structures since Roman times is reinforced concrete. Concrete is a mixture of cement and groundstone, and then it is reinforced through the use of a fibrous material, which can be almost like fiberglass, or steel rods called rebars, which are put into the concrete while it's still wet, that helps prevent cracking. It has had widespread use since the 19th century, and it's typically concrete is then poured into a form so you can make basically any shape you could possibly want. An example of the use of reinforced concrete is the Sydney Opera House from 1973, located in Sydney, Australia. These large sort of semi-spherical domes that sit on top of the structure are all cast concrete, reinforced concrete. And it is one of the most recognizable pieces of architecture in the world, located, on the water as you enter into Sydney. When the Swede Jorn Utzon, who designed it, was thinking about it, and sort of this, Sydney is a town that is sort of built from shipyards and sailing vessels and trade. And so he really did think about trying to make the Opera House look from the outside like a boat, like a ship with sails. And so these big, structures made out of reinforced concrete and precast ribs were made to sort of look from a distance like this sailing ship, entering into the harbor outside of Sydney. Uh, Postmodernism basically began in the 1980s, and it was a reaction to all of the modernist architecture that had happened before it. Postmodernism combines the hard rectangles of modernism with new materials that they didn't have previous to 1980, and features of styles from the very ancient past. This is the Humana building in Louisville, Kentucky. It is designed by the architect Michael Graves. And as you can see, it, has a lot of the same architectural characteristics that we've seen before. These look very much like, skyscrapers, using post and lintel structures, the use of the arch, as a way to sort of hold up, you see at the very top, these large structures. It almost looks like you've stacked Greek temples one on top of the other to create the structure. Our book even continues to tell us how Graves has sort of mixed these historical styles and references together to create something new. You have the implied columns, the portico, the cornice and triangular glass structure, which is like the pediment that we talked about on top of the Greek temple. And you also have sections that seem very Baroque, these sort of curved portions of the upper building. Another example of postmodern architecture is the Quadracci Pavilion, which is located in Wisconsin. And again, you can kind of see how this is sort of using sort of, kind of a range of different kind of architectural forms to the Greek temple, along with, again, this sort of the way boats are actually put together, sort of forms an architectural structure that looks very different than anything that precedes it. Today in the 2000s, architecture has really not changed a lot. The one thing that has changed architecture is sort of our interest more in green architecture, architecture that is self-sustaining, concerns over limited resources, energy conservation, and sustainability have become the most important issues. So now a lot of architects they don't have a choice, and they want to sort of create these buildings that are more eco-friendly. Buildings such as this, like these tiny houses that are designed by Michelle Kaufman. This is called Glide House, which is built by a lot of materials that have been recycled from construction sites, are examples of how modern architects, or contemporary architects, I should say, not modern, contemporary architects, are sort of using materials in a new way, right, to try to create homes that are smaller, more efficient. People are not as interested in building these grand mansions as they have in the past. Everyone is more interested in creating buildings and structures that are better equipped in a contemporary setting. Kaufman actually, looks at this as an inexpensive alternative to costly California homes. It's based on a prefab module made of sustainable wood. It has double pane windows, roof solar cells, and again, as I said earlier, it is made completely out of recyclable materials. And that ends our lecture on architecture. We will be looking at a lot more architecture in this class and talking about, in particular, a lot of great architects from Frank Lloyd Wright to Frank Gehry next week. But, if you have any questions, you can reach out to me at cakers@lee.edu. Thank you.